This lesson is on circular motion. Let's draw the diagram now. Now, this is a light rod which is free to rotate in a vertical plane about one end O. A particle of mass m is attached to the other end A. At any time, the velocity is in the tangential direction. When the rod makes an angle theta with the equilibrium position, the velocity is v. Now this system moves under conservative forces only. For a system of bodies moving under conservative forces, we can apply the principle known as principle of conservation of energy. As we consider only the mechanical energy, we can call this principle as principle of conservation of mechanical energy. First of all, we can apply this equation to the particle, that is, impulse equals change in momentum in the horizontal direction. The impulse is I. Now, what is the change in momentum? Before the impulse, the velocity of the particle is 0. Now, just after the impulse, the velocity of the particle is u. Then, after the impulse, the momentum in the horizontal direction is mu. That is mu. Then, what is the initial momentum? That is 0. So the change in momentum is mu minus 0. That is mu. Mu. Let that equation be equation number 1. First, we should know how to apply this principle. This is the initial position of the particle and the rod. This is the final position. When we apply this principle, we have to equate the initial total mechanical energy to the final total mechanical energy. Now, what is the mechanical energy? Total mechanical energy is the sum of the potential energy and the kinetic energy. Now we have to find out the sum of the potential energy and kinetic energy in the initial position and equate that to the sum of the potential energy and kinetic energy of this final position. We can draw any horizontal line and assume that the potential energy on that line equals 0. Now I have drawn a line through the center of this circle and assume that at this level the potential energy is 0. Now what is the initial potential energy? That is minus mga. Length of the rod is A, minus mga. Now the initial kinetic energy equals half mu squared. Final potential energy equals minus mga cos theta. Minus mg into this side. This is a cos theta. What is the final kinetic energy? That is equals half mv squared. Half mv squared. Then initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. Then we get this one. M cancels out. When we simplify this, we get this equation. Let that equation be equation number 2. From this equation, we can get the velocity of the particle at any angle. Now, for this to describe complete vertical circles, the velocity of the particle at this point, the highest point, should be greater than or equal to 0. This is the equation we got earlier. Now using this equation number 2, we have to find out the velocity of the particle when theta equals 180. Let that velocity be v1. We substitute for theta. We substitute 180 for theta. Then we get v1 squared equals u squared minus 2ga 1 minus, when theta equals 180, cos theta is minus 1. We get minus 1 here. Then we get v1 squared equals u squared minus 4ga. So we get v1 equals square root of u squared minus 4ga. Now, for this to describe complete vertical circles, v1 should be greater than or equal to 0. That is v1 square, that means square root of u squared minus 4ga greater than or equal to 0. So u squared minus 4ga greater than or equal to 0. Therefore u squared greater than or equal to 4ga. Therefore u should be greater than or equal to square root of this one, that is 2 into square root of ga. Now, for this to describe complete vertical circles, u should be greater than or equal to square root of ga. If this just travels a complete vertical circle, what is the condition? What should be the condition? That is u is greater than, no, not greater than, u should be equal to 2 square root of ga. That is the velocity. This horizontal velocity should be equal to 2 square root of ga. Then this particle just describes a complete circle. Now, in this problem, we are asked to find out the minimum value of the impulse for this to describe a complete circle. For this, we have to we want this equation. We got this earlier, I equals mu. That is, impulse equals mu. Let the minimum value of the impulse be m1, I1. Then I1 equals m into 2 into square root of ga. That is 2m square root of ga. This is the minimum value of the impulse. Now, then we also have to find out the tangential acceleration when the rod is inclined at 30 degrees to the vertical. That is, when theta equals 30, what is the tangential acceleration? Now let us find the tangential acceleration at this point. Now this angle equals 90 minus theta. I have produced this line. Now we apply F equals ma, that is Newton's second law of motion, to this particle in this direction along v. Then the force along this direction is minus mg sine theta. That equals m into the acceleration. When the velocity is v, the acceleration along this direction is dv by dt. dv by dt. Now this is after the time t. This diagram I had drawn, it is after the time t. That is, acceleration along that direction is tangential acceleration dv by dt. Therefore, dv by dt equals, this cancels out, m minus g sine theta. Now, when theta equals 30, dv by dt equals minus g sine 30 minus g sine 30. What is sine 30? 1 or 2. That is minus g by 2. Now, this is the tangential acceleration in the direction of v. Now, in the opposite direction, that is equal to g by 2. Is equal to g by, along this direction is equal to g by 2 units of acceleration. Now, we have to find the positions of the rod when the tangential acceleration is 0. This is the acceleration in this direction when theta when the rod makes an angle theta. Then we have to find the position of the rod when this is equal to 0. d by dt equals 0. This is equal to 0 when minus g sine theta equals 0. That is sine theta equals 0. That is when theta equals 0 or 180 degrees. At this point, when the particle is at this point, the tangential acceleration is 0. Also, it is 0 when the particle is at B.